welcome to the series on complex analysis. This is the third and final session on the extended complex plane. This session is optional. You can omit it, you don't need it, but if you want to go for higher studies, especially in topology, geometry, or higher aspects of complex analysis, this may be a beginning point, okay, which it will give you a glimpse of what lies ahead in modern geometry. Okay, and so see, this one tries to explain what really happened behind the scene. We define holomorphic functions from C infinity, that is extended complex plane, to C. Okay, it's not ad hoc. Okay, in fact, I gave toward the end, I even told you a subtle point to show that it's not ad hoc point. Okay, now I want to abstract it and make it very explicit. Okay, that will be the stepping stone or baby steps towards a fantastic universe which awaits you. Okay, so let us get started. So as I said, please notice that this is optional. Okay, so let's start with, okay, uh, a topological space. Okay, let's assume that there exists an open set. Okay, there exist two open sets, so let me call it, this is my X and this is an open set. Okay, no, all these things are there. Okay, and this is another open set. Okay, so what we are assuming is that X, okay, is union of U1 and union U2. Okay, and U1 intersection U2 may or may not be empty. But if X is connected, then it has to be U1 intersection U will be non-empty. At present, I don't need that. Okay, okay. Now let's further assume there exists. So this is, let me call this is an U1. Let me call this. So therefore, this is U1, and the other one is U2. Okay, this is a common thing. Let us look at the common thing. Give some name. This is the common thing. This is U1 intersection U2, right? Now what I'm going to assume is that assume there exists a homeomorphism of this onto some open set V1. This is your phi 1. Okay. Now let's assume there exists another open set V2. Okay, and this is the map phi 2. Okay, these are all, everything is contained in C. Yeah, so what are our assumptions? Let's just write it briefly so that you know X is U1 union U2 Uij open sets. Next, okay, there exists homeomorphisms. Okay, phi j from where? Uj to Vj. What are Vj? Vj's are open sets in C. Is that okay? Now suppose I have a function. Okay, I am running out of colors, so let me just say this is a function into complex plane. Okay, maybe I should I don't think it's complex plane, it's better to draw only simply like this. See, and suppose I have a function f from x to c, right? F is a function from x to c. I want to say f is holomorphic. Okay, I want to define this to to define. Okay, this is a standard trick. Okay, right. Now let's look at this map. See, what we know is I know how to define holomorphic functions from an open set subset of C to C, right? Now let's look at the picture. There is an obvious way you can look at this. There is a map, this one, which goes this way, which is phi inverse, and there is an obvious map here which goes this way, phi 2 inverse. Because remember, they are supposed to be homeomorphisms, therefore it's in particular bijection, therefore phi 2 inverse will be a bijective continuous map homeomorphism from B2 to U2. Yes, do all of you agree? So I am going to say F is holomorphic okay around a point, let us say around x in capital X, or let me say it's first differentiable. F is differentiable at x. If okay, this is what I want to define. What I do is, suppose I find an x, suppose my x happens to be here, right? Then I know there is a corresponding z1 here, right, which correspond to this x under phi 1, right? X phi 1 of x equal to z1, or phi 1 inverse phi, this is phi 1, sorry, phi 1 inverse of z1 is x. Is it clear, right? Therefore I say it is differential to x if the map f composite phi 1 inverse from v1, which is phi 1 of u1, to c is differentiable. At which point? At z1, namely phi of x, right? Because look at this, I have a map from v1, that is phi 1 inverse, then followed by f, that is going to be a map into c, right? Therefore what I have done, so this is a map from, this is a function from an open set V in C to C, therefore I can talk about its differentiability at a point, and z1 is a point which corresponds to x under the map phi 1. This is again phi 1, I forgot to write. Is it clear? And suppose if x belong to, suppose x belong to here, so again the same thing, I don't know why this happens. Suppose now my x happens to be here, right? Then I can again say this, I say f is differentiable at x in x if x belong to u2, then f composite phi 2 inverse from b2, which is phi 2 of u2 to c, is differentiable at z2, which is equal to phi 2 of x. Again look at the picture. So I have x here, there is going to be a z2 here, right? So phi 2 inverse followed by f is going to be a map from v2 to this, therefore I can talk about its differentiability at z2. Alright, now all of you are essentially masters students, at least you're more or less finishing BSc, so you have an obvious question to ask. Okay, yeah, ask yourself the question because I can't hear you, but you know what is the question to ask. What is the question to ask? Question to ask, suppose if x belong to u1 intersection u2, suppose it's non-empty, the x may belong to this. Then okay, one of you may say f is differentiable at x if f composite phi 1 inverse is differentiable at phi 1 of x. Other person will say f composite phi 2 inverse is differentiable at phi 2 of x, right? So is it consistent? Is it well defined? So question is this notion well defined? Because what may happen is f composite phi 1 inverse may be differentiable at phi 1x, but f composite phi 2 inverse may not be differentiable at phi 2x, or the other way around, right? So somehow I have to make sure, okay, this definition is independent of where x belong to. X may belong to u1, u2. If x is equal to union xi ui, then x may belong to some many ui's, but still the answer will be correct. Are you understanding the question? Okay, now let's try to understand this. Again, let us go to the picture. Okay, now suppose z is here. This is my z, x which is common. Okay, this is my x, right? Now you can see there is this u1 intersection u2 will be somewhere like this. This may be my phi 1 of u1 intersection u2, right? This is an open set n capital X because u1 and u2 are open, right? And this is u1 intersection u2 is open in u1 as well as x, because u1 is open in x, therefore u1 intersection u2 is open in x also, right? Now phi 1 of that, because phi 1 is a homeomorphism of u1 onto v1, phi 1 of u1 intersection u2, namely this set, this must be open in v1 and hence in C, right? Because this is an open subset of v1, but v1 itself is an open subset of C, therefore phi 1 of u1 intersection u2 is open in C. Do you understand this? Yeah. Now a similar thing happens here. What is the thing? So this one under phi 2 may be like this. Okay, this may be phi 2 of u1 intersection u2. Again, for the same reasons I explained, this will be open in v2 and in C. Do you understand? Right. Now I want to look for this map. So I start with some z here, okay, and via phi inverse I go. Where will I go? I'll go to some point here, right? This z goes to some point here, right? Now under phi 2 it goes to some point here, right? Maybe I should use a different colors. So this is my z that goes to this point, and that, and okay, this is under phi 1 inverse, and then that goes to this point, right? Because phi 2 maps this u1 intersection u2 onto this set. Do you follow? Therefore, what do you think I have finally got? I have got a map from this to this set. I have a map from this set to this set. Keep the picture in mind. That's why the blackboard will be good. I can draw half of the blackboard and keep it in mind here, but unfortunately I can't do that here. Okay. So finally, what do I end up with? I'll keep the picture. So this is, and this is, okay. So I go from here and come here. Okay. This is phi 1 inverse, and this is phi 2. This will be my u1 intersection u2. This is the picture I have. Okay, so the map is going to be phi 2 composite phi 1 inverse from where phi 1 of u1 intersection u2 to phi 2 of u2 u1 intersection u2. You understand this? And these are open sets in C. Right? Now notice that this phi 1 inverse will map this homeomorphically onto this, and phi 2 will map this homeomorphically onto this. Therefore, this map is a homeomorphism. Yeah, just pause, review. I should have done earlier in my thing to finish in time. This is what happens. Okay, I went without stopping. Yeah, right. So now notice that it's a map from where to where, from an open set in C to open set C. Suppose I demand, okay, we demand phi 2 composite phi 1 inverse, okay, is holomorphic. Where? From the set phi 1 u1 intersection u2 to phi 2 u1 intersection u2. Actually it is to C, but then it takes values only here. You understand? Now I can ask a similar thing. What will I do? I can go the other way around, right? So I go from here to here, take any point z here, and then okay, under phi 2 inverse, I will land in u1 intersection u2, and this is phi 1 inverse, and this will be phi 1. I will land here, right? Therefore I have also map, because I can interchange 1 and 2. Similarly, phi 1 composite phi 2 inverse is holomorphic from phi 2 of u1 intersection u2 to phi 2 of phi 1 of u1 intersection u2. Keep the picture in mind so you will not get confused. Okay, when I do that, if you have a pen and paper, draw the picture on your hand so that you will keep it in mind, so it is easy, right? Notice that this is a bijection, right? This is a bijection. Okay, therefore you can also see phi 2 composite phi 1 inverse, if you want, okay, if you call it xi, okay, and xi inverse is phi 1 composite phi 2 inverse. Is that clear? Right? So in some sense this map xi is something like an isomorphism for me. Isomorphisms in complex analysis. What does it mean? It is a bijection, and itself, it and its inverse, both are holomorphic. So how do you define isomorphism between topological spaces? It must be a bijection. The function its inverse must be continuous. In complex analysis, I want it to be the function its inverse must be holomorphic. Okay, that's like if you want to call it analytic isomorphism or holomorphic isomorphism or holomorphic homeomorphism or analytic homeomorphism. Okay, there is no standardization here. You just call it. So intuitively, it's an isomorphism when I want to talk about complex analysis. Right? So when do I say two open sets in complex planar isomorphic? If there exists a bijective map between them such that each way the map is holomorphic. Is that clear? Okay, suppose grant this. So suppose, assume this happens. Phi 2 composite phi 1 inverse and phi 1 composite phi 2 inverse are holomorphic, that is isomorphism. Okay, then our concept of differentiability is well defined. Because if I look at f composite phi 1 inverse, okay, is differentiable at phi 1 of x, right? Now let's look at f composite phi 2 inverse. F composite phi 2 inverse, okay, this is this I can write as f composite phi 1 inverse, okay, composite phi 1 composite phi 2 inverse, right? Do you follow? By assumption, this is holomorphic, therefore this is holomorphic, this is holomorphic, therefore the composite is holomorphic, therefore this is holomorphic. Do you follow that? If it is differentiable at x, simply differentiable at x, right? Are you following? So I will say simply holomorphic if it is holomorphic on the domain of definition, right? Then, are you following this? Yeah. So what do I want to show? I want to show this is differentiable at phi 2 of x. Now this is differential at phi 2 of x, right? For any x in u1 intersection u2, right? Are you following? Yes. And then what do I have? Phi 2 inverse is differentiable at phi 2 of x, and where will I land? I will land in some point in here, namely x. Okay, therefore this will be at phi 1 of x, but f composite phi 1 inverse is differential at phi 1 of x. Okay, are you following this? Yeah. Okay, this is just a chain rule, but if you are worried about at a point, if you do not know, because I can imagine some of you will have difficulty, simply assume differentiable on u1 intersection u2, right? Then this is going to be differentiable on u1 intersection u2, this is differentiable, okay, and this is differentiable, this is going to be differentiable on phi 2 of u1 intersection u2, right? Therefore this will be differentiable. Are you following? Please pay attention. Okay, please go through this once again. So if this map is called the transition map, that is phi 1 composite phi 2 inverse or phi 2 composite phi 1 inverse, that is I transit from here to here. Okay, so if they are isomorphisms, then we can define a function f from x to c or an open set u in x to c, okay, when it is holomorphic on u. Okay, this is the upshot. Okay, it may be tough, please go through it. These are the chain rule, you should learn how to do that. Okay, I hope all of you know how to compute the derivative by using chain rule, so you just plug in, then you will get it. Okay, right, don't be lazy, don't be lazy, please do that. Now let's go back to what we did. So this is exactly what happened. We see infinity, I wrote it as two sets. One is u infinity and another is u0. U infinity is an open set containing this. Okay, and u0 is simply c star. That is, notice that this u infinity is nothing other than c infinity minus 0, and this is C infinity minus infinity, that's it. Yeah. Now I have a map. Now, if I want to call it phi infinity from u infinity to c, what are the map? Phi infinity of z is 1 by z if z is not equal to infinity, otherwise 0. Okay. We have seen this is a homeomorphism. Okay. This we saw in the first lecture itself. And similarly, let's look at phi 0. This is u0 to c. Again the map is the same. Phi 0 of z is 1 by z for z not equal to 0, otherwise is to infinity. Sorry, I'm sorry. I got carried away. Phi 0 of z is z. There is an obvious isomorphism of u0 to this, namely it goes to here, right? This is also to c. Are you following? So these are homeomorphisms. This is also a homeomorphism because the identity map restricted to, right? Now what is u infinity intersection u0? That's precisely c star, right? Now let's compute what are the maps phi infinity composite phi 0 inverse. Now remember phi 0 of z is z, therefore it is simply phi infinity of z, which is 1 upon z, because what is the range of phi 0? It is c star, therefore z cannot be 0, therefore it is 1 by z. Do you understand? Right. And what is phi 0 composite phi infinity inverse of z? Now there are two things. Okay, if z is not equal to infinity, then what do I have? This is going to be phi 0 of z, which is, so phi 0 of 1 by z, that is equal to 1 by z, right? Phi infinity, go back, what is phi infinity inverse? That is, for z not equal to 0, phi infinity inverse is 1 by z, yeah, because phi infinity's inverse is itself. Okay, and suppose it's 0, sorry, it's infinity, then what happens? Okay, but remember, sorry, that's it, because the domain of this, so see, domain of these things, transition map phi 0 inverse or phi 0 composite phi infinity inverse is c star, therefore z is not equal to 0 and z cannot be infinity also, right? You follow that? So just to make sure that you understand, let me go through phi infinity of phi 0 of z, where z is in u infinity intersection u0, that is going to be phi infinity of z is just z, that is 1 by z, because this is c star, right? Therefore z cannot be infinity. And similarly phi 0 of phi infinity of z, now z is in c star, therefore it's going to be phi 0 of 1 by z, that is also 1 by z. Do you follow that? Therefore the transition map is the map xi from c star to c star, that is whatever you want, phi infinity of u infinity intersection u0, which is same as phi infinity of u infinity intersection u0, to that this is z going to 1 by z. This is a bijection and holomorphic each way. Therefore when I want to say a function f from some domain in U to C infinity to C is holomorphic on U, okay, what all I have to do is look at for each Z in U, look F composite phi infinity inverse is, okay, holomorphic, or F composite phi 0 inverse is holomorphic. If you want, simply differentiable at Z. And okay, so this is my C infinity, okay, so I look, one point is removed, this is my 0, okay, this is my infinity, okay, you follow that. So this is my 0, so this is my U infinity intersection U 0, right? So suppose I start with anything, any open set, okay, suppose this may be the open set, okay, then I can take the point to be here in this, that is included infinity but 0 omitted, or infinity omitted 0 included, everything is there, okay, I'm not, you understand that? So differentiability of the function f at z is independent of whether you are checking differentiability via f composite phi infinity inverse or f composite phi 0 inverse. This is what we did. If you remember, I said if z belongs to some neighborhood of u containing infinity, okay, and z is not equal to infinity, then I said f differentiable at z, there are two ways of checking. One is f composite phi inverse, other one is simply f. Ordinary standard definition, this is using phi. Do you remember? That's where I ended the subtle point in the last lecture. Okay. So as I said, this is optional. If you ventured into that, that means you are keen to go for higher mathematics. So go through this. Okay. This is a baby step towards Riemann surface, manifold theory, and modern differential geometry. This is the very first initial step. Like a baby, begin to take the first step. Okay. So these are things which are not explained. As I said, point at infinity is in 5 minutes they dispose of. Okay, holomorphic at infinity or analytic at infinity, they dispose of in 5 minutes, less than 5 minutes, most often just a definition, right? Whereas we took lot of time to explain, because I think we are in 21st century, we should try to go forward. Okay, we should not try to do what happened in 18th century or 19th century when people were struggled. But you can see what are the things we used. All the Riemann's idea, okay, helped us to understand this. In fact, it helped us to launch very many new concepts and subjects like Riemann surfaces and manifolds, modern differential geometry, everything. All the genesis because of this. Okay, I hope you enjoyed. We'll meet again on some other occasion. Take care and stay safe.